George and I are somewhat concerned that if I use the laser pointer here, we will blind two of the key experimentalist observers. So, so I was going to stand up, but if I stand up, George will never get me sitting down again. So maybe we will try and work things this way. So the theme of my remarks is emergence of all sorts. The emergence of the CMB from the seven veils of the foregrounds and extragalactic sources that's celebrated in the peeling back. And I'm going to also celebrate the emergence of the seven pillars of CMB power spectrum. We haven't got one yet, and we may never get it, which is the tensor to scalar ratio. The emergence of the standard tilted dark energy, cold perhaps, dark matter model. And one of the things that I know my thesis advisor, Willie Fowler, and presumably this other gentleman here, Fred Hoyle, would be infinitely pleased about is the absolutely perfect agreement with Big Bang nucleosynthesis. What we have is 380,000 years reaching back to the first 3 minutes. That is an amazing story. Forget the dark energy, forget the dark matter. That is one of the amazing victories of our subject. So then I'll turn to something which is the driven vacuum, the acceleration that happened way back when, with, I think, increasing evidence, and currently now. Not only that, it seems that it is a differential change in the acceleration. And yes, Jan, I'm trying to fulfill the promise of December. We were wondering in our press release back in December what to emphasize. This turned out to be a little too complicated, perhaps, to do, but I think it's one of the very interesting things that there's evidence in the ultra-early universe that that the acceleration is not just going on, but that it has to have changed. It has to be changing. Now, the other point that I think I would really like to make, we can compute all of these things in great detail, as you saw, but if you think, if I think, if Slava thinks he understands it, I say, think again. Because what we're dealing with is not the garden old vacuum that inhabits this room with us. It is not a garden vacuum. But we are dealing with one in which gravity is inextricably linked to that vacuum and drives it. That is the nature of the development of the fluctuations of the universe, but also the entire framework of the inflationary process. That is very deep, and I would say that we work with it, but to think that one really intuitively understands it, maybe Slava will explain it to us again. And yet the paradox is we do work with it, and we know more about the early inflation dynamics than we do about late inflation dynamics, and I'm going to try and demonstrate that as well if I can figure out how to. It's the middle button? Okay, but first of all, I'm going to go back to the seven pillars, and I'm not going to go through them, but I am going to remind my illustrious colleague here of these curves from 87 and how everything fell into place. It's an amazing story from our theoretical perspective of how our colleagues, experimental colleagues, have delivered an amazing story. We, in those days too, Wendy, we had H a little wrong. Just kidding. Okay, the pillars, right? We're going, ups and downs, damping tail, all of these things found in step. The Gaussianity, incredibly maximally random for a given CL. Secondary anisotropies, now it's a great victory of the subject with so much information in it. The EE polarization spectrum revealed, and even more so in what's to come. What we haven't got, of course, yet is the gravity wave signal. And so, celebrating with our great friend here, would that he were here, and as a Planckian and an actor, and with very good friends who are W-mappers and SPTers, what an amazing thing that is. And what an amazing thing this is. And that's the pillars. Okay, you think this is one of the classic bond over subscribed things. These are a collection of reconstructed scalar power spectra from the early universe, and you will recognize this as from the Planck inflation paper. And the power spectrum, it's actually a deviation power spectrum relative to a best fit, depends upon a stiffness parameter. And so, you know, how much stiffness you put in, you get a certain amount of oscillations, and a point was made about that anomaly. This was something, we never ever published things, with Shiji Wang that we did in pre-ACT data. And there was, in my view, a very nice paper that we were on, Lozek et al., using the ACT data. And that was really pretty neat because it was showing that, you know, you could sort of make out that there was first of all, almost a straight line there with the ACT data, where you can understand that something interesting is coming. So this does exactly what we did here for the Planck data. Planck plus WP plus SNLS, which plays no role in this, plus BAO. And this is not a fit to these. These are done as a cubic spline mode. There are 9 knots, which means a lot more parameters than NS, DNS, D long K, etc. And these are trajectories, 1 sigma sample of trajectories, and this is the best fit. And that is a power law. And it emerged from the data, and that is an amazing thing. And then this is not a fit to this line. This is the best fit from the parameters paper, the best fit power spectrum in the simplest model. So just to make sure that you are startled by how outstanding that is, that's over many orders of magnitude. What happens down here, we've seen it a lot in the different data, is that these kinds of power spectrum trajectories do feel the low L, what happens at low L. What I will not say is that we know exactly what's going on here. I sort of doubt that they're sort of making a big feel on that 217 anomaly around 1800, but they might, who knows. But this is the thing to celebrate. It's an amazing thing because you see things are flanging out where the information isn't very good, but there's a regime in which it's really quite perfect. And what is rather interesting about being able to do things, so the gravity waves were turned on in this as well, is that you can use information like this to reconstruct the acceleration history of the early universe. And so that's what the next slide purports to do. And so this is 1 plus the deceleration parameter. Yeah, 1 plus the deceleration parameter. And the thing that allows us to go over 8 E-folds is the fact that the resolution, as measured by the wave number, is intimately related to the dynamics. And so these are trajectories, and it's really quite regular, and it's in my view, quite nice. Another aspect of this diagram, which has been shown again and again and again at this meeting, is a line that sort of went undiscussed, but it is an amazing line. This is uniform acceleration is determined by that epsilon constant deceleration parameter. And look at how much white space there is in here. This was emerging, a lot of white space anyway. What that means is there has to have been a change in that. This is the way the acceleration looks now with, again, the supernova. So, you know, that's subject to change. So we're going from deceleration into acceleration as we go now. And our probe is only about 1 E-fold. And I won't describe this in detail, just to say that's pretty good. And one can translate that into the 1 plus W kind of figure. And this reminds us why Planck is such a powerful set of data. Here, unfortunately, with the current supernova data, it wants to have 1 plus W less than 0. That's supercritical acceleration. Those are silly models. And we always include them, but they're silly models. And it's very difficult to make them work. You can do a little bit of fooling around, but really, we should be having a prior on our trajectories, which says that we must have W greater equal minus 1. Okay, and so that goes to that. And then just to leap forward to a potential future, which will be Planck 2.5 years of data, when CHIME and Euclid are online, a figure like this might womp down into a really quite brilliant set of trajectories that focus on zero. So again, the issue is acceleration trajectories. Those are the mysteries, and the mysteries are there in the ultra-early universe and the current universe, and that is really the story of the emergence that we have and we have to deal with.